Today we will discuss for 2-hour planar robot the end effector velocity space, mapping end effector velocity space, tip point velocity space under given joint velocity, considering initial posture this way. One link is L1 this way and the other link is L2 this way. So L1 makes an angle 0 with horizontal line and L2 makes pi by 2 angle with this line. So theta 1 equal to 0, theta 2 equal to pi by 2. For general, for any angle theta, suppose this one is L1, this one is L2, it makes theta 1, it makes this line with angle theta 2 with this line. So considering this one is x-axis, say x1 cap, this one is y-axis, say x2 cap. X coordinate of this point and effector is L1 cos theta plus this one as a whole, this one angle is theta 1, this one is theta 2. So it makes theta 1 plus theta 2 with x1 cap. So L2 cos of theta 1 plus theta 2 at that instant, at that position. X2 is L1 sin theta plus L2 into sin of theta 1 plus theta 2. So if we take derivative with respect to time t, x1 dot, say x1 dot, it is dx1 by dt, rate of change of x component of this point and effector. So L1 into minus sin theta 1 into theta 1 dot, which is d theta 1 by dt, L2 into minus sin of theta 1 plus theta 2 into theta 1 dot plus theta 2 dot. So expanding this, minus L1 theta 1 dot sin theta 1 minus L2 theta 1 dot plus theta 2 dot sin theta 1 plus theta 2. Similarly, if we take derivative with respect to time t for both the sides, so dx2 by dt, it is denoted as x2 dot. So L1 into cos theta 1 dot plus L2 into sin cos of theta 1 plus theta 2 into theta 1 dot plus theta 2 dot. So L1 theta 1 dot cos theta 1, L2 theta 1 dot plus theta 2 dot cos of theta 1 plus theta 2. This represent velocity, x component of its velocity, end point, and these represent y component of its velocity, tip point velocity and effector velocity. So these two readjusting in matrix form, this one and this one, x1 dot x2 dot equal to minus L1 sin theta 1 minus L2 sin of theta 1 plus theta 2. This is first element of first row, and this one is minus L2 into sin of theta 1 plus theta 2. Second element of first row. This one L1 cos theta 1, L2 cos of theta 1 plus theta 2, this element, and this one L2 cos of theta 1 plus theta 2 into theta 1 dot theta 2 dot. So simultaneously we can write this term and this term in matrix form. This is Jacobian matrix, this one. Now we are considering initial position theta 1 0, theta 2 pi by 2. So if we put theta 1 0, sin 0 is 0, but theta 2 is pi by 2, so theta 1 0 plus pi by 2 is sin pi by 2. So this term is 0, but this term is 1. So minus sin of pi by 2 is also 1. So this term as a whole minus 1, see here. For this initial posture, and this one, if we put theta 1 0, theta 2 pi by 2, L1 L2 we have taken 1, L1 and L2 both. In our example, we have taken 1. So minus L2 is 1, sin of pi by 2 is also 1, so it is also minus 1. And this one, if we take theta 1 0, cos 0 is 1, so 1 into 1 is 1, but here 0 plus pi by 2, so cos pi by 2 is 0, so as a whole this term is 1. Here theta 1 is 0, theta 2 is pi by 2, so 1 cos pi by 2, but it is 0. So Jacobian matrix for this initial posture, we want to find possible velocities in this condition at this initial moment into theta 1 dot, this one, theta 1 dot, theta 2 dot. So first row, this column, so minus theta 1 dot, minus theta 2 dot. Second row, this column, 1 into theta 1 dot, 0, 0, so theta 1 dot. So this gives x component of its velocity at that instant. So minus theta 1 dot plus theta 2 dot into x1 cap. It is the unit vector in x direction. And theta 1 dot x2 cap, it is the unit vector in y direction. So it gives y component of velocity at that instant. It gives x component of its velocity. If we consider theta 1, theta 2, the range of theta 1 and theta 2, this one, this one, theta 1 dot, theta 2 dot belongs to closed interval minus 1, 1. That is joint velocity, angular velocity between minus 1 and 1, including minus 1 and 1. So if we draw this range in xy plane, say this one is theta 1 dot axis, this one is theta 2 dot axis. So this point is 1 comma 1, this point is minus 1 comma 1, this point is minus 1 comma minus 1, and this point is 1 comma minus 1. So all boundary point as well as inside the square, each and every point are in this range. So for this range at theta 1 dot, theta 2 dot, what is the velocity x1 dot, x2 dot? What is the velocity of tip point and effector point? See here, theta 1 dot, theta 2 dot both belongs to closed interval minus 1, 1. So theta 1 dot plus theta 2 dot addition also belongs to minus 2 to 2 because of minus 1 less than or equal to theta 1 dot less than or equal to less than or equal to 1, and theta 2 also minus 1 less than or equal to theta 2 dot less than or equal to 1. If we add these two terms, we get minus 2 less than or equal to x1 dot this one. So this one x1 dot less than or equal to 2. So x1 dot, the range of x1 dot is this, minus 2 or 2 between them. And this one y1 dot is theta 1 dot, and we know that y1 dot as it is theta 1 dot from this minus theta 1 here. So theta 1 dot is minus theta 2 dot minus x1 dot. Using this we can replace theta 1 dot by minus theta dot minus x1 cap, x1 dot, sorry. So x1 dot plus x2 dot is minus theta 2 dot. So, but theta 2 dot is minus 1 less than or equal to x, less than or equal to theta 2 dot less than or equal to 1. So opposite of this is also in this range. So minus 1 less than or equal to x1 dot plus x2 dot less than or equal to 1. This one x1 dot, but x1 dot is vx. Suppose this is rate of change of x coordinate. So this is velocity, x component is velocity, and x2 dot is vy. So this one, splitting this one, isolating this one, minus 2 less than or equal to vx, x1 dot is vx, and vx less than or equal to 2. From this minus 1 less than or equal to x1 dot is vx plus x2 dot is vy is less than or equal to 1. So separating this, minus 1 less than or equal to vx plus vy and vx plus vy less than or equal to 1. So we have 4 inequality, this one, this one, this one and this one. The point, the intersecting set of these 4 inequality gives the velocity space of end effector. So this one equation we can write this way: vx plus 2 greater than or equal to 0, equation number 1, vx minus 2 less than or equal to 0, and this one equation vx plus vy plus vy plus 1 is greater than or equal to 0, equation number 3, and from this vx plus vy minus 1 less than or equal to, we are mapping end effector velocity, this point, for this initial posture, that is theta 1 equal to 0, theta 2 equal to pi by 2, and given that joint velocity theta 1 dot, theta 2 dot belongs to closed interval minus 1 and 1. Under this joint velocity space, what about the end effector velocity space? So we have at last, using this mathematics, we have 4 inequality. 1, 2, 3, 4. So from this, how can we map the end effector velocity, which is actually parallelogram? So see here, just we are removing inequality sign. So we will draw the lines vx plus 2 equal to 0. Here vx plus 2 is greater than or equal to 0. Now here vx plus 2 we have taken 0. and then after we will plot satisfying this inequality. Similarly for this Vx minus 2 less than or equal to 0, but initially we are taking Vx minus 2 equal to 0. Similarly for this one, third inequality, Vx plus Vy plus 1 is greater than or equal to 0, but we have taken equal to 0. And Vx plus Vy minus 1 less than or equal to 0 already, but we are taking equal to 0. So we will draw these four lines on Vx Vy plane. This one, this axis is Vy axis and this axis is Vx axis. So if we plot these four lines, Vx plus 2 equal to 0, that is Vx equal to minus 2. So this one is Vx plus 2 equal to 0, this line. And the other line is Vx minus 2 equal to 0, that is Vx equal to 2. So 1, this is Vy, this is Vx, this is 1, 2. So this is Vx equal to 2, this line, Vx minus 2 equal to 0. And the third line, Vx plus Vy plus 1 equal to 0. To represent line we require at least 2 points, minimum 2 points. So if we take Vx 0, if we take Vx 0, Vy is minus 1. See here, if we take Vx is 0, Vy should be minus 1. So 0 comma minus 1, this point. And if we take Vy 0, we get Vx minus 1. So the point corresponding to it minus 1 comma 0. So this one is minus 1 comma 0. This is 0 comma minus 1. So this line represent Vx plus Vy plus 1 equal to 0. And the fourth line, Vx plus Vy minus 1 equal to 0. So if we take Vy 0, Vx is 1. If we take Vy 0, Vx is 1. So 1 comma 0, this one point, 1 comma 0. This one is 1 in distance. If we take Vy 1, we get Vx 0. If we take Vy 1, Vx should be 0. So 0 comma 1. So these 2 points. So this line represent Vx plus Vy minus 1 equal to 0. This is Vx plus 2 equal to 0. This is Vx minus 2 equal to 0. And this is Vx plus Vy plus 1 equal to 0. Now using inequality, Vx plus 2 is greater than or equal to 0. And this is Vx plus 2. So if we put origin here, 0 plus 2, it is greater than or equal to 0. So satisfying the point satisfying the inequality, this equality is on this line or this direction. Similarly, the other inequality is Vx minus 2 less than or equal to 0. So if we put 0 comma 0 here, it satisfied Vx minus 2 less than or equal to 0. So the point on the line as well as this side satisfying this inequality. And the third inequality is Vx plus Vy plus 1, this one, third inequality, Vx plus Vy plus 1 is greater than or equal to 0. And the line is Vx plus Vy plus 1 equal to 0 is this. If we put origin here, 0 comma 0, it satisfies 0 plus 0 plus 1, 1 is positive. So the point in the direction of origin, the point lie on this line as well as in this direction, satisfying third inequality. And the last is Vx plus Vy minus 1 equal to 0. But here Vx plus Vy minus 1 is less than or equal to 0. So if we put origin here, 0, 0, minus 1, 0 plus in left hand side, 0 plus 0 plus minus 1. So it is minus 1, it is less than 0. So the point on this line as well as towards left, towards the origin, satisfying this inequality. So condition satisfying this and this. The intersecting set is parallelogram. This one, A, B, C, D. So we have proved under the range theta 1 dot and theta 2 dot belongs to closed minus 1 1. the velocity space of end effector gives the parallelogram. So point inside the parallelogram as well as on the line, these are the possible velocities, direction as well as magnitude. So in this initial posture, point can move in any direction. It is freedom. This point can move in any direction, and this any direction. There are infinite direction. So it can move this point. This one is L1, this one is L2. It can move this way, 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 this way. But in certain direction, magnitude are constrained. Suppose in this direction I want this velocity, then no problem. But in this direction I want beyond this much of velocity, I can't achieve. But in all direction it can move. But we can find corner point directly. See here, this x1 dot is minus of theta 1 dot plus theta dot, and x2 dot is theta 1 dot. So if we take theta 1 dot is 1, theta 2 dot is 1, then x1 dot x2 dot minus 2, 1. Similarly, theta 1 dot is minus 1, theta 2 dot is 1, so x1 dot x2 dot, if we put here, we get 0 minus 1. If we take theta 1 dot corner point minus 1 and theta 2 dot also minus 1, if we put here these two value, we get plus 2 x1 dot, and for this minus 1, 2 comma minus 1. And the last corner point of square, theta 1 dot is 1, theta 2 dot is minus 1. If theta dot is 1 minus 1, so 0, and here theta 1 dot is 1, so 0 comma 1. So this is minus 2 comma 1, this is 0 comma minus 1, this is 2 comma minus 1, and this is 0 comma 1. These are the vertices of the parallelogram velocity space in end effector velocity space. And this one is joint velocity space. Theta 1 dot versus theta 2 dot versus theta 1 dot. Theta 1 dot comma theta dot belongs to closed to minus 1. So under this joint velocity space, we get end effector velocity space as a parallelogram. So here in this condition, the end point can move in any direction. Okay. I am demonstrating. See here. Now I am demonstrating. This one is fixed pulley. This one is movable pulley. This one is link having length 1 unit. This one is also 1 unit. L1, L2. This is initial posture. Theta 1 equal to 0. Theta 2 equal to pi by 2. In this position, we want to find end effector velocity. And we have studied the end effector velocity, this end point L1, L2, it can move in any direction, but constraint about magnitude, so it forms parallelogram, but it can move in any direction. So I am demonstrating this tip point velocity can move in any direction. Initially I want to move this point in this direction. This is fixed pulley. So see here, observe my effect. See here. This way, this way, this. See here, this is fixed pulley, but I am, see here, the joint velocity, see, this way, 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 this way. It will not move. This end point velocity is not well. This point is stationary, but it is rotating only. But this point is movable pulley, movable joint. So I can move in this direction. Initial posture is this. So I can move in this direction also, this way, and this way. I am trying to just this way, this way, this way. But if I want to, this one is 90 again. I am repeating. Then I can move in this direction also. This is fixed joint. This is fixed joint. It cannot move, but it can rotate. And this is movable joint. So in this it can move this way, and it can move this way also. This is also. So in any random direction, I can have velocity of this tip point. Suppose I want to move this point in this direction, parallel to this. Then also it is possible. See here. See. This is fixed. See. Up to certain limit, this way. And from this, From this, I can move this way also. See, tip is descending this way directly. So in this initial posture, at that initial posture, this point can move in any direction. Now we will map the end effector velocity space under the condition joint velocity space theta 1 dot theta 2 dot in such a way that theta 1 dot square plus theta 2 dot square equal to 1, unit circle condition. But for the same initial posture theta 1 is 0, theta 2 is pi by 2. Under this condition, we want to find end effector velocity space, this point velocity, tip velocity. We have already calculated x1 dot y x2 dot is -1 for this initial posture, 1 0, theta 1 dot theta 2 dot. So x component's velocity is this into this minus theta 1 dot minus theta 2 dot, and this into this y component's velocity, tip velocity, it is theta 1 dot. So minus of this theta 1 dot plus theta 2 dot into x1 cap, it is x component's velocity, and theta 1 dot x2 cap, it is y component's velocity. But now we have changed the condition. Initially we have discussed the theta 1 dot theta 2 dot in under unity, within unity, but now theta 1 dot square plus theta 2 dot square is 1. So at this initial posture, we want to find what about the tip and effector velocity space. So x1 dot is vx, which is minus theta 1 dot plus theta 2 dot into bracket, and x2 dot, it is y component's velocity, which is called theta 1 dot. So theta 2 dot, subtracting theta 2 dot from this, minus theta 1 dot minus vx, and from this theta 1 dot is vy. So theta dot is minus theta 1 dot minus vx, and theta 1 dot is vy. So theta 2 dot is this one minus theta 1 dot minus vx, but theta 1 dot is vy, this one. So minus vy minus vx. So as a whole, theta 2 dot is minus of vx plus vy into bracket, and theta 1 dot is vy. So eliminating theta 1 dot theta 2 dot using the equation theta 1 dot square plus theta 2 dot square is 1. That is vy square plus this much square equal to 1. See here. So theta 1 dot square plus theta 2 dot square is 1. But theta 1 dot is vy square. Theta 2 dot is this square. But minus 1 square is plus 1. So vy square, expanding this, vx square plus 2vx vy plus vy square, which is equal to 1. So re-adding term and adding terms, vx square plus 2vx vy and this 2vy square, which is equal to 1. This equation in xy plane represent an ellipse. So I have drawn, after solving this equation, this one. This is vx axis, this is vy axis. That is x1 dot axis, that is this one is x2 dot axis. So this is the end effector velocity space. Here also, because we have considered the same posture. So tip point, this one and this one, at this initial position, tip point can move in any direction, but the constraint about magnitude gives ellipsoid. This ellipse is referred to as manipulability ellipsoid, and this one is major axis, this one is minor axis. The closer the ellipsoid is to a circle, that is the closer the ratio L max by L minimum is 1 is to 1, the more easily the tip move in arbitrary direction, and thus the more removed it is from a singularity. This one. Now I am demonstrating. Suppose this one is fixed joint, this is movable joint. So in this condition, we have considered theta 1 and theta 2 are equal. So in this condition, the tip velocity can move in this direction or in this direction, perpendicular to this. Either except this direction, it cannot move in any direction. Suppose I am adjusting this way, So at that instant, tip velocity cannot move in this direction. In this condition, it move perpendicular to velocity this one. But after a short while, it can move in a direction. But in this posture, at that instant, when theta 1 and theta 2 both are aligning same, then tip velocity, this is fixed joint, this is movable joint. It cannot displace, but it rotates. So tip velocity cannot move in any direction, either only it can move in perpendicular to this line, this way or this way. Except that direction, it can't move in any direction. But at that posture only, after short while, somewhat change, then after it can move any direction. This is singularity.